In this example, we're going to analyze a rational function algebraically, and we're going to determine any zeros, holes, vertical asymptotes, and horizontal asymptotes for this function. So to start, we're given r of x, and it's the quantity 4x minus 8 over the quantity x squared plus x minus 6. And the first thing that we want to do is to simplify this function as much as we can. And to do that, we'll factor it and see if there's any common factors in the numerator and denominator. So to start, let's write our original function. And so I'll factor that numerator, and that's just linear, so it's just 4 times the quantity x minus 2. And that denominator is quadratic, and it'll factor into x plus 3 and x minus 2. And so we can see that the numerator and denominator both have that factor of x minus 2. Another thing that we want to note is that, and I'll note this off to the side, we're not asked to do this, but we do need to keep track of it, is that the domain of this function, if we look at this original, that denominator cannot have -3 or 2 in it, or this function won't be defined. So our domain will be the set of x such that x is not equal to -3 or 2. Now, as we go through simplifying this, we need to make sure that we have the exact same function, and in doing so, it has to have exactly the same domain. So when we simplify this, we're going to find that r of x is equal to 4 over the quantity x plus 3, but we have to list the restriction that x cannot equal 2. So that's a domain restriction that we're listing, and the key there is that this 4 over x plus 3 still requires that x can't be -3, but if we don't write that x is not equal to 2, we've changed the domain and that would give us a different function. So in simplified form, r of x is 4 over the quantity x plus 3 given x is not 2. Okay, so going along, we're going to look for zeros of this function. And again, just from a numerical perspective, to get a 0 when we have a rational expression, we need 0 divided by a number. I'm using 5 arbitrarily, but 0 over 5 would give us the number 0. So we have to have 0 in our numerator in order to get 0 as an output. And in this particular case, we have 4 in that numerator. And there's no variable value that we can input for and get 0 out. We're always going to have that constant 4. So what that means then is that for the zeros, there are none. There are no zeros for this function. All right, and so we've got the zeros checked off. And let's go to vertical asymptotes. So vertical asymptotes, we're going to see those occurring anytime this rational expression has a 0 in the denominator. And the reason is that if we take something like, let's take 5 over 0, that's undefined. But what's more so is that if we put in a number really close to 0, we'd get a really large output. So we're going to see these vertical asymptotes occurring where some numerical value tries to cause division by 0. And what that means then is that we can't input that value. So at that x value, we're going to see a vertical asymptote. So here, we want to make sure that we go to the simplified form. And you'll notice that I have a real number over 0, and that's going to be, whenever we see that case, that's going to be where we see a vertical asymptote occurring. So in this one, we're going to see that happening at -3. And so the equation of that vertical asymptote will be x equals -3. Now we'll note that we don't look at the factor in that earlier form because we wouldn't actually get a real number divided by 0 for 2. So if we plugged in -3, we'd get 4 over 0, and that's what's going to make us have that vertical asymptote of x equals -3. But at 2, there's something different happening. So the function's still undefined at 2, but it's not going to have a vertical asymptote there. What we're actually going to have at 2 is a hole. And that's related to the fact that we had that factor of x minus 2 in each, that numerator and denominator. So the function's undefined at 2, but it doesn't have a vertical asymptote. And what that looks like on the graph, so holes, in this case not plural, so we can just have a singular one. We just have a hole. And there's a hole at x equals 2. If we wanted to think about, so on a graph, a hole is just going to look like a place where the graph goes along, and then there's one point excluded, and then it continues. So if we wanted to know exactly where that point occurs, we would look at where does what is the y value of this function near to? And so if we plugged in 2, we would see that we have 4 over 2 plus 3, so 4/5. So if this function were defined at 2, it would pass through 2 comma 4/5. So what we're going to see is that that open circle is just going to occur at 2 comma 4/5. That would be the point where that hole is. Okay, and the last thing that we'll look at will be the horizontal asymptote. And the horizontal asymptote is dealing with that long run behavior. And a couple different ways we can go with that. If we look at the cases of the degree of the numerator and denominator, we can see here that the degree of the numerator is 1, that leading term is 4x, and the degree of the denominator is 2 because that leading term is x squared. So looking at that, we can see that the degree of the numerator is less than the degree of the denominator. And so what that means then is that our horizontal asymptote will be y equals 0. And that's coming from the degree of the numerator is less than the degree of the denominator. All right.